This week I will once again cover the necessary functions to complete problem set 4. My apologies if last week's video was a bit confusing. Today I will try to make it as clearly as possible the functions you will need to complete this problem set. So to begin, again, this code can be found at my GitHub at the following link. I want to install dplyr because I use the dplyr package in order to solve the problem set. If you open up your RStudio workspace, what you'll see sometimes is this little bar up here that says a package is not installed. So that is an alternative method to install packages rather than use the code here on line 6. So I will actually just click install and it should work. It should install it. And if you just give that a second, it will install the dplyr package, and then I'll be able to run this line on line 7, which is dplyr. And as you can see down here, actually, RStudio is currently downloading the package because it's not running my code currently. And so while that installs, I will show you that we are downloading the data directly from GitHub. You'll notice that there's no CSV file here, and that's because the CSV file is already in my GitHub from last week's lesson. And so what I want to show you, and I think I've showed you this before, is that you can download a CSV file directly from GitHub, which is really nice. A lot of COVID-related data is on GitHub, so you can download it for analysis, and I just want you to remember that you can do that. So we save the URL where that CSV file is, and then we download, we read that CSV function over the URL. So I've just broke this into 2 steps, but you could do it into 1, and what you'll see is now we have the data frame with our data that we want to use. Of course, you can download it by actually using the CSV file as well. And we can show that. Now, going back to the dplyr package, now that it's been installed, we can run the dplyr library function, run it twice just to see that there's blue, because these red is just warning messages. And it looks like if we were to, again, run it many times, you'll see that it's blue and it's working. So now we can use the dplyr function. And so now moving into 1.1, what we want to do is, for problem 1a, is calculate the standard error and the confidence intervals. So the standard error can be calculated through this simple equation. It's just the standard deviation divided by the square root of n, which is the number of observations. So this example, I'm going to use age, but on the problem set, all you have to do is replace all these with education, and then you'll get the answer. So it shouldn't be too hard, but please let me know if you have questions. So this example, again, is for age, but you want, for the problem set, you use education, ed. And you would change that for, of course, all the code down below, too. So we will first calculate the standard deviation. It looks like it's saved up here, so that's saved. And then we calculate the number of observations, so it's the length function, and then the data that we're using. So again, in this example, I'm using age. So n calculates that. And now we want to calculate the standard error, which is just the standard deviation divided by the square root of n. So again, standard deviation here, and here, and then we take the square root. This is a square root function. And then we calculate it, and that will be our standard error. Now, again, I just break this all up into steps. If you wanted to, you can actually just all do it at once by, doing df age divided by sd, or excuse me, square root, and then the length. Oops. Well, see, that's why I do it in steps, is because it's a little bit easier when you do it in steps. It's a lot easier to see what you're doing. And And so I'll just clear this out and show you that this is the equivalent. So standard error calculation in steps is the same as doing it all at once. But I'll erase that and just leave this as is because this is the information that you'll need in order to find the standard error. Again, just replace this age with education to get the correct answer. Again, we're doing the t-score, and for the answer, all you do is, actually I should probably do age here for this example, but when you run the code for yourself, put in education, and this just gets the t-score. So when you run this line of code, you'll see that the t-score is now saved, and it's 1.963. And now we want to calculate the mean, which I call x bar. And again, I'm saving these so it doesn't come out in the output, but if you wanted to see your saved variables, all you have to do is look to the upper right corner. And so now we have the information to calculate our confidence intervals. So we just take x bar minus the t-score times the standard deviation. So exactly how it is in this formula here. It's mean plus or minus, so plus in this instance, or sorry, minus in this instance because we're doing the lower confidence first, minus the t-score that we calculated here, multiplied by our standard error. And this is our standard error here. So it's exactly this equation formula that we're using. So lower confidence, we'll run here. So our lower confidence level, it will be 20, and our upper confidence level will be 21.26. So that is the answer for age, but of course, your problem set is asking for education, so just go in and change this to education, and you should get the answer. Now, I showed you a brief introduction to functions last week, and I think it was probably pretty confusing, so you can skip over this if you don't want to listen, but this actually will give you the answer. It's exactly what I calculated above, but in a function, so I call it an answer function, and it's doing the same calculation that I just did above, standard deviation and standard error, t-score, everything, but it's just doing it all at once because it's a function. So if I save this function, I saved it as answer function, as you can see up here. It says answer function, and what I'm going to do is put in our data, df, and then select the age column. And when I run this function, it will give you the exact answer that I just got below, but actually it prints it off in a little bit cleaner of a manner. So if you go ahead and use this answer function and you put in education, this will actually be the answer to 1A. So if you want the answer via this function, then please try it out. And you can obviously cross-check your answer by using this too. But you have to run the whole entire function, it's code, in order to save it. So just be careful when running that. You want to see it right here. Okay. Now we will move on to t-testing, and we are going to start with the two-sided t-test for one mean, which corresponds to problem 1b, and we are going to start off by specifying an age that we're interested to know if it is statistically different than, if the mean is statistically different than whatever age or whatever data point that we're interested in seeing. So I am interested in whether the average or the mean age is statistically different than 30, and the alternative hypothesis is, of course, that it is not 30. And so what I do is first I save this age variable, and then I do the t-test, and the first data that I put in is the data for age, and then whatever data that I want to compare it to. So in this case it's 30, but I saved 30 as this age variable, so it's the same. And so when I run this t-test, you'll see that we have a very, very, very significant t, which means that the p-value is extremely small. Just to be clear, a couple of students have asked me about this. T-value and p-value are extremely they're related. I don't want to say they are the same thing because they're slightly different, but they operate in the sense that if the t is low, the p will be high, and if the t is high, the p will be low. So they both show whether a test is statistically significant or not. So in the case that it is significant, just remember the t score will be high and the p will be low. In this case, it's extremely low, so we can reject the null hypothesis that the mean is 30. And that makes sense because the mean of the data we actually know, it's actually 20. And so it does seem quite not impossible, but quite unlikely that the mean is actually 30. The only way that would be the case is if we had an extreme amount of if our standard deviation was quite high for our data, but it's not, and we found that out with this t-test here. And again, this is a two-sided t-test. And that corresponds to 1b. So 1c is more or less the exact same type of problem, but instead of using the same exact age in your data set, it's education, we will use a different age. So it's exactly what we did up here. We save this new age, and that will go to 22, and then it's the exact same code. And in your data, in your problem set, you're going to be using education here and education here, and then changing this mu here. So we run this corresponding 1C problem here, and I will clear the data just to make it a little bit more clear. And what you'll see is that it's still we can still reject the null that the mean for age is statistically different than 22. So if we were to actually set that to 20, we would see the same thing. So that covers the two-sided t-test for one mean. Okay, so those were just one means that we were testing for. Now we're going to do the two-sided t-test, but with two means. And so the first thing we need to do is separate our data. This filter function is actually dplyr, and a couple of students were actually curious about how to do the alternative method, so I will show that as well. The way you, and I will show that below. So first I will show dplyr, excuse me. And so what I want to do is filter out this ABD, which is a column in our data frame. And ABD stands for abduction. So 1 if it's abducted and 0 if not abducted. So filter will just show the entire data frame, but only with those who have been abducted, as you can see here below. But I want to save that into a new data frame, and then I'm going to show that data frame. And what you'll see is that this data set consists of those who are only abducted. And now I want to do the same thing, but for non-abducted, and I will place a 0 in there. And again, I'm saving the data here by naming it whatever I want it and placing the equal sign there. So I did that for those who have not been abducted, and I'm now showing that data. And as you can see, ABD is 0, so that's all the data for people who have not been abducted. And after we have done that, we can conduct a t-test comparing we can compare their ages and whether the means of their ages are actually statistically the same or different. So I will write the name of that new data frame that we made, and I will select the age column. For your assignment, you will just, all you have to do is change these and run it to education. But I just want to show you age for the example because I don't want to specifically give you the answer yet. If you're curious, please email me and I can help you out. So anyways, now all we have to do is to conduct this t-test. And if you're confused about what we're doing here, just always check to see what it is that we're putting into it. And what you'll see is all we're putting it in is data. But these data are age data for the two different groups. So it's comparing whether the data is the mean of this data is actually statistically different. And so let's clear this before we run it. And we run it and we'll see that that the t-test is quite high, so we can reject the null hypothesis. Now, what exactly is the null hypothesis? Well, I put it up here just to be a little bit more clear. It's the mean of age abducted minus the mean of age non-abducted equals to 0. So this means that there is no difference between the two groups, right? There is no difference. But what we actually find is that if you look down here, because the t-test actually calculates the means as well, there is actually a difference between the means. And so when we run the t-test to check whether that is statistically significant or not, we find that indeed, yes, it is statistically significant, which means by extension, we can accept the null hypothesis, or that there's evidence for the null hypothesis, that the mean of age and the mean of age for abducted, the mean of age for non-abducted is not equal to 0. So for your example, it's the mean of education for those who have been abducted, and the mean of education for non-abducted equals to 0, and then the alternative is not equal to 0. But just try to really think slowly when you run these tests to ensure that you're actually understanding what it is that you're doing in R. And so that was actually using dplyr to filter the data. Some students have asked, again, as I mentioned briefly beforehand, how to do it without using dplyr. This is the code here, and you're going to want to change this to education. But so this 2.321 is exactly the equivalent to 2.32, but it is filtering the data. It's filtering for those abducted just in one line. So if you look at that, that's all the age data for those who have been abducted, and that is all the age data for those who have not been abducted. And so if we run this, you'll see it's exactly the same outcome. Now we will move on to the problem for 1F. And it's actually very similar to what we did previously, but again, the abducted, actually this is the answer. So I'm actually giving you the answer to 2.31. It's because I'm selecting the education data rather than the age as we've been doing before. And so if you run this, you will see that again we have a incredibly significant t-statistic, and what this says is that actually this is yes, what this says is that the true difference in means is potentially greater than 0. And so it's just a little bit different than the two-sided mean for the two means t-test that we did above, because the alternative hypothesis above in this example in 2.32 was two-sided, and in this case it's one-sided with the alternative being greater. So that is the big difference there. And so I think the professor will cover in a little bit more detail in his lectures the difference between those two. And So I will just cover the last problem here. And it's again a two-sided t-test with two different means, but in this case we will be using father's education. So again, I'm just using this DF abducted data and DF non-abducted data in order to do it, and 2.4 actually this is the answer as well. So you can get the answer right there, and that will show you that actually there is not a statistical significant finding. The p-value is quite large here, and so there is not evidence for this alternative hypothesis that the true difference in means is not equal to 0, which means that we could not reject the hypothesis that the two means were equal. So these t-tests are a bit tricky. You really have to go in and look at it very carefully. Just to drive this point home, I'll go back to 2.32 to show you when you're running a t-test, right? So like in 2.32, I have this example up here. The mean of age abducted minus mean age non-abducted equals to 0. And then I showed the alternative hypothesis. But this data is actually available in the output of your t-test. And so what you'll see here is the t, the degrees of freedom, the p-value, and then you'll always see this alternative hypothesis. So the true difference in means is not equal to 0. It's exactly the same as I have there. So if we reject it, then there is evidence for the alternative hypothesis. And true difference in means is not equal to 0 is just an incredibly fancy way to say the means are different, right? Statistically different. And so don't get too freaked out about this here. Just kind of stop and think about what it means, and then just remember that you're dealing with means too. So the means are actually listed here below, just in case you were interested. So again, this is incredibly difficult material to learn. It's not intuitive. Please do not give up. Just ask questions. It takes a couple of times for you to understand it, and I think that I will try to help out in any way I can to try to like visualize this, but please just ask a lot of questions and show up to office hours. Thank you.